So basically, we are discussing the continuous functions which are linear. So the function which is linear and its domain is finite dimensional non-linear space, then such a function is always continuous function. So that we discuss before this theorem, and then in this theorem we are discussing when a function defined on non-linear space is continuous. Right, so in general we are not assuming that x is finite dimensional, x may be infinite dimensional basically in this theorem, because if x is finite dimensional and f is linear, then such a function is always continuous. So when we have a linear function from non-linear space x to non-linear space y, it is continuous if and only if this last condition is satisfied for some positive number alpha, and all of these conditions are equivalent to this condition for this quotient map. So quotient map f is a given linear function. F is a given linear function. We will define associated map f tilde by quotienting x by kernel of f, and this function given linear function f is continuous if and only if the kernel is closed subspace of the domain and this f tilde is continuous. So f tilde is continuous with respect to the quotient norm on this quotient space. So we discussed that this condition is equivalent to this other condition of continuity. So sometimes we will use this proposition later on, and we discussed several examples also of continuous as well as discontinuous functions which are linear. So in the first example, we discussed the differential operator is discontinuous. That means that is a linear map, but it is unbounded. So here we have considered on the domain supremum norm, and codomain also we consider the supremum norm. Domain is one times continuously differentiable function, and codomain is continuous function on closed interval 0, 1. So this was the first example where we have seen that we cannot find alpha basically. After that, we discuss functionals. So examples of functionals. So using this differential operator, we can define several functions. The first function is derivative evaluated at point x equals t is equals to 1. So that is a scalar valued function. Therefore, it is called functional, and that is not continuous. That we verified. After that, we verified that on C00 we can define this linear function, and this function is also discontinuous with respect to the supremum norm. Right, on C00 we can define two norms, in fact three norms: supremum norm, one norm, and two norm also we can define. So with respect to supremum norm, we have discussed that this is discontinuous function, right? And with respect to the, just a minute. Yeah, so with respect to the supremum norm, we have seen that this function is unbounded, and next we have verified that with respect to the one norm on the domain, this function is in fact continuous function. Yeah, so in this case, when it is continuous, for that part, we have verified that alpha it turns out to be 1 in that case. Okay, so then we discuss homeomorphisms. Homeomorphism is a map which is continuous. Its inverse is also continuous from the range. And the first condition for existence of inverse is that the function should be injective. So that condition is very important. The function should be injective, and we are discussing linear functions. So this is the first theorem that f is linear and it is a homeomorphism if and only if there exists alpha and beta such that the linear function f is bounded above by alpha and bounded below by beta. Right. So that is the terminology we are going to use. If num of fx is less than equals to alpha times norm x, then we will say that f is bounded above by alpha, and similarly when there exists beta such that norm of fx is greater than equals to beta times norm x, we will say that the linear function f is bounded below by beta. Okay, so now we will see some application of this result. So using this result, we can show that all finite dimensional vector spaces are complete. So we proved this result in the last lecture and we stopped there. So let us see one corollary of this result. So we will assume that in the starting I mentioned that all the linear functions defined on finite dimensional non-linear space are always continuous. So this is the in this corollary we are going to use that result. So let x be a finite dimensional non-linear space. Right. So our domain of the function. So we know that f is a function from x to y, be a linear function where y be a another non-linear space. So y may be x also, y may not be x also. May be different or it may be same. So whenever we have such a function, the first condition which we want to prove is that f is homeomorphism is a homeomorphism if and only if f is bijective function. So here homeomorphism is homomorphism onto codomain y. So this condition is equivalent to the condition that our linear function is bijective. So what this result says that if we take any linear function which is bijective, bijective means 1 1 and 1 2, if and only if f is also continuous, inverse is also continuous, provided x is finite dimensional. We'll show this, we'll prove this result. Second condition which we want to prove is that all norms on x on the domain are equivalent. So equivalent means each norm is so we are taking any two norms, then yes, so let us write down that we have the first norm and the second norm. This is first norm, we have second norm. these two norms are equivalent, that means the first norm is stronger than second norm, and the second norm is stronger than the first one. So we have discussed that when this happens when the norm of x is less than equals to alpha times norm x dash for some alpha. Similarly, on the other way around. So any two norms on x are equivalent. We'll show that in this part. And the third condition is that all finite dimensional vector spaces are complete. So using this, any two norms are equivalent. We will show that every finite dimensional non-linear space is complete. So we know that Rn and Cn, they are complete non-linear spaces, right, with respect to the modulus norm. But in general, we don't know all the finite dimensional vector spaces are complete or not. So in this third part, we'll prove that as long as our vector space is finite dimensional, whatever norm we take on that finite dimensional vector space, that vector space is always complete. So that means every Cauchy sequence converges in that. So let us prove this result one by one. So first part is that if our domain is finite dimensional, right? X is a finite dimensional, and we have homeomorphism if and only if f is bijective. So one part is trivial, that if f is homeomorphism, which is homeomorphism means we know that it is an injective function and it is also onto, then it is always bijective, right? So the forward part in the first part is trivial by the definition of homeomorphism. We need to prove only the converse part. What is the converse part? Converse part is if f is a function from x to y, x is a finite dimensional nonlinear space, and if f is bijective, then we need to prove that f is a homeomorphism. So to prove f is a homeomorphism, the first condition is f is injective. That is clear because it is a bijection. So only two things we need to prove: f is continuous and f inverse is continuous. So is it clear that f is continuous? If f is bijective, then f is continuous. So what is the hypothesis? Hypothesis is that x is finite dimensional. So we discuss one result that if we have a linear function defined on finite dimensional nonlinear space, then that is always continuous. So that we are going to use here. So since f is linear function defined on a finite dimensional nonlinear space, f is continuous. So we proved this result that any linear function on whose domain is finite dimensional normally in the space, it is always continuous function. So that we are using here. Now for converse, for to prove the homeomorphism, we need to prove is that F inverse is also continuous. So since F is a bijection from X to Y, it is its inverse is defined on whole Y, right? And we have also discussed that since F is linear function, F inverse is also linear function, right? So moreover, since F is linear bijective function, F inverse from Y to X is also a linear function, right? And what can we say about dimension of Y? Whether Y is finite dimensional or Y is infinite dimensional? We have a bijective function. F is a bijection, so F inverse is also bijection. So if F is a bijection from X to Y, which is a linear function, so that means basically it is a homomorphism of vector spaces. And if X is finite dimensional, what can we say about whether Y is finite dimensional or not? So do you recall any result regarding every linear function maps linearly independent set to linearly independent set? So this is a linear algebra question. Yes, Anurag.
So it will be finite, sir.
It will be finite, yeah. So yeah, okay. So the result basically is that the function should be injective, right? If we have an injective linear function, then it maps in linearly independent set to linearly independent set. So that result we can use, and that will help us that Y is also finite dimensional. So also Y is finite dimensional. So therefore F inverse is also continuous, because F inverse is a map from a which is a linear map, and again the domain is Y, which is finite dimensional non-linear space. So F inverse is also continuous. So basically, whenever we have a bijective map whose domain is finite dimensional, its codomain is always finite dimensional because it is a linear function. So linearity we are using here, F is linear, and then we are using this dimension result from linear algebra. So if F is not linear, this result is not true. You can try some example. So the first condition does not hold if F is not linear. So that means you take any function f from some nonlinear space to nonlinear space Y, X is a finite dimensional. It's bijective, but it is not a homomorphism. So yeah, so try that example. So linearity is very important here. Without linearity, we cannot get the first part. Again, second part, what we want to show that any two norms defined on X are equivalent. So let us start with two norms we are defining on, and to apply the first part, we will need a bijection. Right. So let's start with two norms. Let this and this be two norms defined on the nonlinear space X. And what is given? X is a finite dimensional vector space that is given. So we have two norms on X. Now to apply the first result, we need a bijection from X to itself. So the simplest map from X to itself, which is a bijection, is the identity map. Right. So consider the map I from X to X. So now defined by, so identity maps is defined as each element goes to itself. Right. This is the identity map, and on the domain we are considering the first norm. Right. So on the domain of I, we assign, so domain and codomain are the same vector space X. On domain and codomain we assign different norms. Right. So on the domain we are assigning the first norm, and on the codomain of I, which is X, on that we assign the second norm. So now we are considering the linear map I, which is a from X to X, which is identity map. This map is always linear function because it is identity map, and clearly the identity map is 1 1 on 2. So note that the identity map I is linear and bijection. It is 1 1 onto linear function. Right. So if it is 1 1 onto linear function, then from first part what we will get, if we have 1 1 onto linear function which is a bijection, then it is a homeomorphism. Right. But here we are getting from X to Y, but in the second part we have a identity map, so it is from X to X itself. So therefore from the part 1 of this corollary, part 1 from this corollary, we get identity map is continuous. Right. So yeah, so not only continuous, it is a homomorphism. So that means I is also continuous, I inverse is also continuous. So now we will use this result, the last part. Whenever we have a continuous function, alpha exists, right? So therefore, I is continuous as well as I inverse is also continuous. So since both of these functions are continuous, what we get, therefore there exist two positive numbers, alpha greater than 0 and beta greater than 0, such that, so first I is continuous functions, so therefore we get Ix is less than equals to alpha times norm x, right? Now Ix is element of codomain, and codomain we have this norm. So this is the second norm, right? On domain we have the first norm. So this is true for all x in X. So this is regarding the I is continuous. Now I inverse is also continuous. So I inverse is continuous. That means norm of I inverse x. So I inverse x is an element of domain. So we have the first norm defined on that. That is less than equals to beta times norm of codomain. Norm of codomain is dash norm, right? Now I is the identity function. That means Ix is x. So therefore I inverse x is also x. So let us substitute these two things here. So what we get is, therefore we get norm of x dash, right? Because Ix is x, that is less than equals to alpha times norm x, and right. And on the other hand, I inverse of x is also x. So therefore we get norm of x is less than equals to beta times norm x dash. So whenever such a alpha and beta exists, such that first norm we can compare with other norm, and the other norm we can compare with the first norm. So in that case we say that these two norms are equivalent. So in other words, the first norm is stronger than the second norm is stronger than the first norm. So whenever any Cauchy sequence converges with respect to this norm, it converges with respect to this norm, and on the other hand, Cauchy sequence converging with respect to first norm, it will always converge with respect to second norm. So that is the use of these norms are equivalent. So that means if we have a non-linear space which is complete with respect to first norm, it is always complete with respect to the second norm, because completeness we discuss in terms of norms, Cauchy sequence, or convergence of Cauchy sequence in terms of norms. So this is the second part, and the third part. So what we proved in the second part? In the second part, we proved that if we have two norms defined on the same vector space, then they are equivalent. So third part, we want to prove every finite dimensional vector space is complete. Right. So we know that on a finite dimensional non-linear space, any two norms are equivalent. Right. So if we can show that one of the norm is complete, the other norm will also be complete. So let us prove the third part. So in the third part, first of all, we need to fix the dimension of x. We know that x is a finite dimension, right? But what is the dimension of that? That will denote by n. So let n be the dimension of x. So x is given n-dimensional vector space. What we want to show is that x is complete with respect to whatever norm we define on x. Right? So we know that what are the complete nonlinear spaces? Rn and Cn. They are finite dimensional complete nonlinear spaces. So if we can find a bijective linear functional bijective linear function from x to Rn or Cn, then we can use that Rn and Cn are complete. Right. So in this course, we are always using this fact. R and C are complete. Using that, we proved Rn and Cn is complete. And now we are proving any n-dimensional nonlinear space is complete. Right. So let us start with Kn. So let Kn be so let Kn with norm 2 norm. Right. So 2 norm means we know that whenever we have x1, x2, xn are elements of Kn. So this x is element of Kn. Then the 2 norm of x is basically the Euclidean norm. So that is nothing but j running from 1 to n modulus xj square. And we need to take its square root. Right. So this is a Euclidean norm. With respect to Euclidean norm, we know that Kn is complete. Right. So recall that Kn is complete with respect to this 2 norm. So Kn is a complete nonlinear space if we can define a bijection from Kn to x, which is linear. So let us simply define it. Since x is a finite dimensional, it has a basis, right? So suppose x1, x2, xn be a basis of x. So x is n-dimensional vector space, so that means it has a basis consisting of n elements x1, x2, xn. And Kn has, we know that Kn has basis e1, e2, en, right? So now we define a function, define linear function from Kn to x. So f is applied on n elements, right? So let's define it on k1, k2, kn, which are n coordinates of kn. So this we are defining as using these elements. So k1, x1 plus k2, x2 plus kn, xn. Right. So this is a linear function. It's linear because we can simply take two such elements, add those elements, and apply f So then it will satisfy the property that, yeah, so there should be two brackets here. Yeah. So we can simply say, verify that f preserves addition of kn and scalar multiplication of kn. Right. So clearly f is a linear function and f is also bijection. Why it is bijection? Why it is injective? F is a linear function. So to check injectivity, what condition we need to verify? So we need to check the kernel is zero, right? So for kernel is zero, we need to take f of any element is zero. So that means right hand side is zero. Right hand side is zero. What is right hand side? That is linear combination of x1, x2, xn. x1, x2, xn are basis elements, right? So any linear combination is zero. That means each coordinate is zero. That means k1, k2, kn is zero, right? And k1, k2, kn is zero. That means this vector is zero. So the elements for which f of that element is zero, that is only zero element. Therefore, kernel of f is zero. So note that kernel of f is zero. Therefore, f is injective. And bijective is very clear because you take any such combination, you can always find k1, k2, kn from those that combination, right? So also f is onto. Clearly it is onto. So basically it is bijective linear function from complete nonlinear space to nonlinear space X, right? So that will give us this. Yeah, so now we can use this part that whenever we have bijective continuous bijective function which is linear, but what we have, that is a homeomorphism, right? So f is a homeomorphism from the first part. And once we have a homeomorphism, we can say that there exists alpha and beta, again using this property, right? So therefore, by using the condition of continuity, we get alpha greater than 0, beta greater than 0, such that norm of fx is less than equals to alpha times norm x and norm of f inverse x is less than equals to beta times norm x for all x in codomain. So codomain is capital X, right? So, so there is confusion. We can say this is y. And this condition will give us that x is complete if and only if y is complete. Right. So now using kn is complete and the 2 norm is equivalent to norm on x, we get x is also complete. So completeness again follows from this continuity criteria. So whenever the sequence xn converges to x in x norm, we can only it converges in kn. So that is what we are using here. That whenever we have a Cauchy sequence in x, that will give Cauchy sequence in y, and that Cauchy sequence in y converges because kn is complete, and that will give us the corresponding sequence in x which is complete. So this is regarding the any nonlinear space is always complete. Now this finite dimensional condition is also equivalent to so is my screen visible? Just a moment. Okay. So the last property we want to see is this result. So what happens is a special case when we assume x is a finite dimensional. We know that if f is any linear function from nonlinear space x to nonlinear space y, then f is continuous if and only if kernel is closed and f tilde is continuous. But whether if we take x is a finite dimensional vector space, do we get any special result in this case? So let us see one proposition. So if f from x to y be a linear map, so here where x is a finite dimensional vector space, not vector space, non-linear space, non-vector space, then the following statements are equivalent. So first statement is that the function f is continuous. And the second statement is that kernel is closed. So here we have two conditions. F is continuous implies kernel is closed. So one part is clear. Okay. So one implies two. is clear from the earlier result. So basically this result we are referring that f is continuous implies kernel is closed. So that is clear. Now the converse is that if kernel is closed, then f is continuous. Conversely, suppose 2 is given, that is kernel of the linear function is closed. So now what we know is we know that x is finite dimensional. So that is what we are going to use here. So the claim is that what is f tilde? F tilde is defined on the quotient map, right? So what we know is x is finite dimensional. If using x is finite dimensional, if we can prove that the quotient space is also finite dimensional, then we can prove this result. So the quotient, to discuss the quotient map, so what we'll assume is we'll not assume this the range is finite dimensional of x. Because we know the rank nullity theorem. So rank nullity theorem says that domain is a direct sum of kernel and the range. Right. So whenever we assume that the range is finite dimensional, we can get that the quotient space is finite dimensional. So let us try to prove this. So suppose the range is that is given that range is finite dimensional, right? So let we have a basis element x1, x2, xm, which generates the range. So let f of x range is a span of, since it is finite dimensional, it is generated by fx1, fx2, fxm. So these are the m vectors in the range whose linear span is the range of x, range of the map. Right. So this is what, this is the range of capital F. F is a linear function. So if range is generated by fx1, fx2, fxn, then what can we say about any general element? So this means what? Therefore, if we take any element of the domain, then fx is a linear span of these vectors. So that means basically it is alpha 1, fx1, alpha m, fxm, right? And yeah, so what are alpha 1, alpha 2, alpha n? They are scalars, right? So now since f is linear, we can take these scalars inside. So it will be f of alpha 1 x1, alpha m xm. Right? Everywhere we are using linearity. F is linear. If f is not linear, all this result will not hold. So now again f is linear, so we can take this in on the other side, this element. So we get x minus alpha 1 x1, alpha xm is 0. So that means what? That means this element is in the kernel. And then we know that if difference of two elements in the kernel, then their quotient spaces are same. Right? So therefore x plus zf is same as, so this element we are considering as a second element, so that is alpha 1 x1 zf. So what does this say? This says we can write the any element of the quotient space as a linear combination of elements of the this combination. So what this says is therefore x quotient zf is span of x1 plus zf xm plus zf, where what are x1 x2 xm, x1 x2 xm are the elements corresponding to these basis elements, right? So since range is finite dimensional, these are the basis elements. Those basis elements gives the corresponding elements which span the quotient space. So therefore, x quotient ZF is finite dimensional, and that will give us the quotient map is continuous. So that is the converse. So let me stop here. Okay, so if you have doubt, now you can ask me.